All right, recording has started. So this is lecture one, part two of signals and systems. And again, I hope you're having a great summer. Um, today, bro. I just recorded the last video past 5 minutes. I'm talking about that because this is a different video. I'm recording this on the same day. I guess. I guess. Okay, 5 minutes later. I don't know. Maybe I should start doing the SpongeBob kind of like 5 minutes later. You know what I'm talking about? Anyways, let's lock in. So when I talk about periodic signals, essentially what a periodic signal is, if you know what a sinusoid is, which you should, a sinusoidal is periodic. All right. So if you take a point in your sinusoid and then you shift it by the period, it should be the same value on the y-axis. That's all the period is. That's all a periodic signal is. So if you take a signal, you shift it by the period, the signal remains unchanged. And mathematically, the way to describe that is like this. Okay, so if you have a certain signal, this is continuous time. It's the same for discrete time too. So if you have a signal, you shift it by t, and t here is the period. Okay, it's the period. The period in continuous time is going to be denoted by capital letter T. So for all t, this is true. Then the signal is periodic. Okay, now you can scale that t by a factor m because sometimes you can, if you scale. If you shift your signal by twice the period, it's still periodic because it's still a multiple of the period. The only thing that happened is when m equals 1, you have the fundamental period, which is the lowest integer value for your period. Oh, sorry, not integer value, the lowest value for your period. That is going to allow your signal to remain unchanged. Okay, but 2t, 3t, 4t, mt, those work as well. Here I have it in highlight. Fundamental period t0 of x at t, smallest value, positive value of t. So that's the fundamental period for a continuous time signal. Now, if you're looking at discrete time signal, you have x of n, and that you take x of n and you shift it by the period. You take x of n, you shift it by n, okay? And n here denotes the period of the discrete time signal. Now, same situation we got going on is we can scale this n by a factor of m, and that's still periodic because it's still a scalar multiple of your initial period n, okay? And you can have periods 2n, 3n, blah, 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 and so on and so forth, okay? The fundamental period is n naught. That's the fundamental period of x of n, and it's the smallest positive value of n. So you can see that these two, both for continuous time and discrete time, they're analogous. Okay. Now, even in odd signals, now if you took advanced functions in grade 12, yeah, advanced function in grade 12, you probably looked at even functions and odd functions. So it's the same thing, except we're not calling it even functions, we're not calling it signals. Oh, by the way, if I'm sniffing on my nose a lot, it's because freaking, I don't know what's going on outside. Like the allergies are going crazy. Okay, so we got even signals and odd signals. So this is the definition of an even signal. So if you take the signal, you put it through a mirror around the y-axis, signal remains unchanged. You have an even signal, parabola. All right, it's symmetric. All right, symmetric. You have this, you have this. If you flip it, nothing changes. Odd signal, there's a minus sign over here. Okay, so if you take an even signal, you put a minus sign in front, it becomes an odd signal. Okay, so definition of an odd signal is cubic function here. You've probably seen this before, but this is how it is. All right. So now, if you were to flip this one, it won't be symmetric around the x-axis. Do you see what I mean? That's an odd signal. Symmetric about the origin. Okay. Now, any signal, that's a general statement. Any signal can be expressed as the sum of its even and odd part. For continuous time signal, we have x of t, which is a total signal, is the sum of the even part of the signal, EV is the even, plus the odd, OD. Okay, now overdose, odd. Okay, so this is your signal. And then the discrete time is x of n, which is equal to EV x of n plus overdose x of n. All right, even and odd part. So now the equation of the even part is given by this. Okay, you don't need to know where this is derived from. Just use it from the get-go. There's no value to your there's no value that you're gonna add to the fact of being human by being able to understand the derivation of how this came up with. You just need to know how to use it. Then you can add value to it. Okay. So this is your even part of x of t. It's given by this equation. Odd part of x of t. Now, quick reminder: x of t here curly brackets, alphabet is t, variable is t, continuous time. The equation is the same for the odd part, stupid, why am I saying? Equation is the same for the discrete part, except we're using square brackets, and now you're using n to denote time. But the equation is the same. Now, given x of n, find the even and odd parts of the signal. So you have x of n, you want to find the even part and the odd part. So to find the even part, you're going to use this definition. Yep. So we are going to find, actually, I circled the wrong thing. If you want to find the even part of the signal, you're going to have to use this equation right here. There you go. We're going to use this equation to find the even part of the signal. Okay, you got x of n, which is given to you. So you need to find x of minus n. You add them both, and then you scale it by half. So that's what we're going to do. We have this signal. X of n is equal to 1 when n is greater or equal to 0. So this is 0, and this is n. So when it's greater or equal to 0, so you have 0, 1, 2, 3, you have a 1. And for other cases, which is less than 0, you have a 0. Okay, so this is x of n. Now, if you want to find x of minus n, again, you're going to take this, put a mirror here, you're going to flip it, and then when you flip it, this is what you have going on. Now, by definition here, when you have your signal, you have it flipped, you're going to add them both. Okay, so this is the addition over here. So this is 0, this is 1. 0 plus 1 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 is 1. 1 plus 1, 2. Be careful, don't be me. I put 1 time. All right, I can do crazy math, but I can't add. 1 plus 1 is 2, guys. Remember that, okay? 1 plus 0 is 1. 1 plus 0 is 1. 1 plus, what's that? Oh. You just caught me mid-sneeze and I couldn't sneeze. 1 plus 0 is 1. 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 And then this is what we have. But we're not done yet because we have to scale this by half. So 1 times half is half. 2 times half is 1. So these are all going to be halves. And this is going to be 1. Okay? But that's the even part of the signal. It looks like this. Now we're going to find the odd part of the signal. So we're going to use this definition to find the odd part of the signal. Okay? And so if we go over here, we're going to notice that the only difference between these two equations is here we have a plus sign and here we have a minus sign. Yeah? So this is my initial signal. This is my flipped signal. Now instead, I'm just going to minus the 2 instead of adding. So 0 minus 1 is minus 1. 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 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 0 is 1. 1 minus 0 is 1. You get the point, right? I'm not going to repeat like a broken record here. Okay, so you do the addition. But now, if you go back to the initial equation, you're going to scale it by half. So you're going to scale it by half. Now, after scaling by half, this is what we have. So we found the even part, and then we found the odd part. It wasn't that hard to do. It was actually pretty simple. Now, after finding these two, we're going to graphically check the fact that the addition of the even and the odd part is equal to x of n. It's a graphical proof. We have the even part of x of n, we computed that, we graphically. We have the odd part of x of n, we computed that graphically. If we add them both, in theory, we should get x of n. So let's test that theory. Let's see if it works. Okay, so this is the even part of x of n, as derived before. Odd part of x of n. So now we're just going to take this one and add to this one. Okay, so you have half, and this is minus half. Half plus minus half is half minus half, which is 0. If you plug into your calculator to check, half minus half is really 0. So you got 0, 0, 0, 0. 1 minus 0 is 1. And then half plus half is 1. So that's why you have 1, 1, 1, 1. I think I talked some bullshit here. Because it's 1 plus 0, not 1 minus 0. I don't know why I said minus, because you're adding the two. But it's still the same answer. 1 plus 0 is... hold on, I'm tweaking. No, 1 plus 0 is 1. That's why we have a 1 here. Yeah, you guys see, I can't do like simple math. I can't add numbers. I can do crazy math, but I can't do simple math. But bear with me here, okay? So these two are going to subtract, so it cancels out. 1 plus 0 is 1, and then half plus half is 1, so that's why you have final answer. And this is x of n. If you go back here, it's the same thing. So that concludes lecture 2. First two lectures, pretty simple. The next couple lectures where we start to ramp things up a little bit. Okay. Again, also, I wanted to say, in the second lecture, if you made it to this part of the video, and then you watched my previous videos before, maybe Electronics 1, you watch the cookies and creme and all that kind of stuff, and you like the way that I explain stuff and all that kind of stuff, and if you want me to tutor you, I will add my Instagram description to this YouTube description that I'll be posting, and you can feel free to send me a message there to talk about how we can make that happen.